this video we're going to go over the electrochemical cell potential, specifically the Nernst equation. So we have the equation here, and you'd use this equation if you had to change the temperature, the concentrations where they weren't standard. So just a forewarning, solids have a unity concentration, so things like copper solid, that would have a unity concentration of 1. So you'll see later how that fits into everything. So this is the standard cell potential, F is the Faraday constant, R is the ideal gas constant, 8.314, T is the temperature in Kelvin, N is the number of electrons, and of course we have the natural logarithm, concentration of products and concentration of reactants. So if we do this example below, we have an equation here, and we have the standard cell potentials and the concentrations of some of the ions, or all the ions in the example. So I think he wants us to calculate the cell potential. So first what we need to identify is the standard cell potential and the number of electrons, because everything else we're given the data, or we can identify quite easily. You may have noticed T, they haven't given us a temperature, so we'll just assume it's standard temperature, which is 298 Kelvin, or room temperature 25 degrees. So for standard cell potential, it's always E right minus E left. So we have to identify which one is on the right and which one is on the left. We always know the one in the right is being reduced. And if you remember oil rig, then we know that oxidation is loss, reduction is gain of electrons. Another way to identify which one is on the right and which one is on the left is the one with the highest cell potential is the one that's reduced. So out of these two, 0.77 is higher than 0.34. So 0.77 is reduced, so it's the one on the right. E cell equals 0.77 minus 0.34. That gives us 0.43 volts. So now that we've established one of the variables, we need to know the number of electrons. Now, thankfully they've already given us the equation, and from that we just need to know the number of electrons involved. So if we just write a half equation, we know that copper is oxidized because it becomes an ion, which means it's lost 2 electrons. So you have C2 plus, then we have those 2 electrons because we've got to make sure that the charges balance. So we've identified that N is 2. So if we write our equation again, we have E cell equals the standard cell potential, which we've worked out, minus RT/NF, which is 8.314 multiplied by 298, all divided by 2 multiplied by the Faraday's constant, which is 9650, multiplied by the natural logarithm of the concentration of products. So for products we have copper, so it's copper, so 0.3 multiplied by, we also have a product of iron 2, 0.45. Because we have 2 lots, it's to the power of 2. It counts as the power, you bring it up. And that's divided by the reactants, which we have, as we said before, solids have a unity concentration, so we disregard copper. For iron 3, we have 2.5 times 10 to the negative 3, and that's got a 2 in front as a stoichiometric coefficient, so we add to the power of 2. We work out this calculation, we should be able to get the electrochemical cell potential at the new concentrations. So 0.043 times 298, 2 times 96500, and that's multiplied by the natural logarithm of 0.3 multiplied by 0.45 squared over 2.5 10 to the negative 3 to the power of 2, close bracket, and we get 0.312 volts. And that's it.